All right, thank you, Stan. Now we have the Metagraph talk, an adventure in types, heterogeneous hardware, and compilers in Dask. It's presented by Stanley Seibert, who joins us from Anaconda. He now manages the open source group at Anaconda and has worked on various things, including Numba, the Rapids system at NVIDIA, and various other parts of the PyData ecosystem. So thank you, Stan.
Cool. Yeah, so I'm excited today to talk a little bit about Metagraph. I haven't had to do a public talk about Metagraph, so this is going to be interesting. I do want to warn people that Metagraph is very experimental. We've been, working on it for a while. But this talk is going to be light on code and heavy on ideas, although there is code behind all the things I'm going to talk about, and there is a link at the end. We have pretty extensive documentation, and obviously this is all open source. But I would say that this is more for people who are interested in the ideas you're going to see, and less for if you need to solve the traveling salesman problem by lunch, you may not want to use this just yet. So I'm going to talk a little bit about what Metagraph is, why we use Dask, our approach to trying to stitch together a bunch of libraries, talk about types and how types factor into this story, talk about our work building a Dask compiler, and conclude with some wish list of things that we wish were easier to do in Dask, or we would love to talk to people about how to maybe improve Dask. So first I want to talk a little bit about some of the benefits that maybe aren't obvious to having what I would call a monolithic software domain. So for example, something like array computing. We are fortunate in Python that if you're talking about dense arrays, there's really kind of one standard binary representation, and there's really one kind of standard API, or at least mostly standard API that we've all agreed on for arrays. A dense vector with a shape, a stride, and a D type pretty much describes your data, and whatever NumPy does is a pretty good subset of operations for arrays. And the advantage of that is that forms a core that you can build an ecosystem around. So things like SciPy, which add new algorithms to NumPy arrays, don't define a new array. They just use the NumPy array. Things like CuPy, which move array computing to another place, in this case, the GPU, can re-implement NumPy's API, even though they have a new array. So you have this kind of interesting approach of what are you trying to extend and how. Interesting to note, something like data frames we have like half of this, or we're almost have this sorted. We need something like a combination of pandas and arrow to kind of get this same level of core that you can build around. But not all software domains are like this. So we're going to talk a lot about graphs, and unfortunately in this talk, graph is super overloaded because Dask has task graphs and whatever, and graphs mean other things to other people. So we're not talking about like your stock portfolio, chart. We're talking about like nodes and edges and networks and that sort of thing. That's what I mean by graphs and graph analysis that we're talking about. So graphs are interesting because you can think of them as a software domain that has no center in the Python space. And this is due to a couple of different features of working with graphs. There are many different ways to work with graphs. There's APIs that are very vertex-centric or edge-centric, or doing sparse linear algebra, or any number of other things. There are many different representations. One of the interesting things about graphs is they're fundamentally sparse data structures. And so there isn't one obvious way to represent a graph, and there are different advantages to different approaches. You can have, you could have a dense matrix, although that would be very space inefficient, or a CSR matrix, or a block CSR, or you could just have edge lists or dictionary. I mean, there are a number of ways to represent the data. And you then throw on top of that, you have many possible hardware targets. You may want to process graphs on CPUs or GPUs or FPGAs or new custom chips. Any of these things may come up. And so you have a bunch of projects. And when you go look out there, I've listed a couple here, but there are actually tons of projects. We did a huge survey at the start of this project of projects out there, and they're all very isolated. Very few of them interoperate with each other, and very few of them cover a substantial fraction of all the things you would want to do with graphs. And so this creates an interesting problem of how do you solve a problem as a user in the graph space without just constantly running into walls of whichever package you pick doesn't do all the things you want. So to try and solve this problem, or at least explore a possible solution for this problem, again, this is a very experimental approach, is we're trying to figure out how to blend graph libraries together. So what we've built in Metagraph is what I would describe as a multiple dispatch system that can you may have a single, from a user perspective, you may be saying, I want to do PageRank. And it can dispatch to many different versions of PageRank depending on where your data is at and what kind of things you're trying to do with it. So this multiple dispatch system is paired with an automatic data translation system. So if my data starts at network X, but the implementation I want to use is ultimately in cuGraph or iGraph or somewhere else, the system will actually be able to convert your graph from one format to another format to pass off to the next library. This means that if you may go into one library to do 3 or 4 operations, and then the next thing you want to do with your graph is not supported by that library, we'll just translate it back out to whatever implementation can do the operation you want to do next. And actually key to all of this is we do have built-in Dask support so that you can build a complete computation from beginning to end that includes graph operations in Dask. And as an additional bit of thing we built on top of Dask, a thing that comes up, especially when you want to do scalable graphs, is you may actually want to compile your graph calculation. You may do a sequence of operations. You may want to fuse them together. And so I'll talk a little bit later in this talk about how that works and why you might want to do that. But that's another thing that we've built into Metagraph. And then the final thing is everything's a plugin. So all of the types, all the APIs, implementations, translators, compilers, everything is extensible. So the core of Metagraph is very small, I would say, and all of the real work can happen in plugins. And this allows you to build out an ecosystem of packages around it. So we'll talk a little bit about how all this works in practice so you'll get a feel for it over the course of the talk. To prove out the idea, we've built plugins for a number of different graph libraries, including things like GraphBLOS and iGraph and CUDA and StellarGraph and a bunch of others, just to make sure the system works. And then we've also built these plugins for a number of API categories. So we haven't mapped every function in every library. We've taken a subset of functions in order to, again, try and test out the system here. So why is Metagraph using Dask? And a lot of what this talk is about is how we use Dask and ways that we wish we could use Dask better and that sort of thing. And one of the things that's surprising is Metagraph is not using Dask for partitioned graph computation in the same way that you may use Dask for partitioned arrays or partitioned data frames for scalable compute. And the reason for that is actually distributed graph computing, because it is a sparse data calculation, is hard. And we've left it to the professionals in the sense that we're not implementing the partitioning. We're letting the library backends, if they are distributed, they can continue to be distributed. But what we do like Dask for is because it has really good support for arrays and data frames. And that's an interesting thing to note, is that people don't start with graph data. People start with arrays or data frames, usually data frames of data that they then turn into a graph. You can almost think of a graph as a view on a relational data set that is useful for identifying transitive relationships. So your workflow, if you're doing graph computing, starts usually with data frames. So Dask is great. It offers great support for loading and working with data frames, especially distributed support. So you can, the distributed IO built into Dask is a great way to load, filter, and then create your graph. Another thing, obviously, Dask is great at parallel task scheduling, and you may have a workflow where you may be doing several graph operations that don't directly depend on each other. So then you can take advantage of Dask to do that work in parallel. And then finally, the fact that Dask encourages you to build a task graph in your code, and then you can manipulate that graph before you compute. That task graph approach is really handy because that lazy evaluation gives you a chance to do inter-task optimization. So if you do a sequence of things, you now have an opportunity to go analyze the whole workflow, find places where you could maybe make different choices or combine things, and then start the calculation. That's something you can't do if you're running traditional Python library that does every step immediately. So let's talk a little bit about how we would stitch libraries together. And one of the key backbones of the system is you need types to describe the data that you're passing around. So in Metagraph, we have what we call an abstract type. And this is really just an equivalence class of types. It's not a base class or any like kind of OOP thing. It's really just you have an abstract type of graph, and then that's just a bucket that you can have many different concrete types that all implement graph for a different system. So Network X has its graph that's saved as dictionaries. iGraph has their own format. A SciPy graph is just a SciPy sparse adjacency matrix. cuGraph has their own format. GraphBLOS has its own format. So by defining an abstract type of graph and then putting these concrete types within it, the system understands that in principle, these could be converted between each other. how exactly it decides to do that, we'll get to, but that's sort of the first part of the problem here. We'll skip the notes on types here. That's getting a little in the weeds, but so once you have some types to talk about data moving through the system, the next thing you want to talk about is algorithms, or in this case, functions. So you might have an abstract algorithm called PageRank, which says, okay, I'm going to take a graph and I'm going to compute PageRank for my graph. That has several implementations potentially. One that expects a network X graph, or one that expects a graph BLOS graph, or one that expects a COOC graph. And again, the user will call just a PageRank function, but it will be dispatched down into one of these. And the interesting thing to note is you might not have one of these for every possible kind of graph someone may pass in. Someone may show up, backing up here, someone may show up with an iGraph and pass that into here, and maybe you don't have an iGraph implementation of PageRank. At that point, you need the system to be able to convert that graph from iGraph format to one of these other ones in order to run it, which we'll talk about here in a bit. So one thing to note is that abstract algorithms refer to abstract types. So you can say that I have a thing that takes a graph. The concrete implementation needs to describe the concrete types it takes, like I need a network X graph or I need a COOC graph. And in both of these cases in the code, we actually use Python type annotations to indicate these signatures. So these type annotations are meaningful to the Metagraph system. And so when functions are registered with the dispatcher, we inspect those annotations in order to understand when we can pass data around, or when we have to convert it. And that conversion is an interesting thing. So if you've been looking around the Dask space for a long time, you may remember a project long ago from Blaze called Odo. Matt Rocklin worked on Odo quite a bit, actually. And Odo was a thing that was designed mainly for trying to translate files on disk, although it did have some in-memory data structures you can see here to move around. And it was this idea of, if I have a graph of translators, like if I know how to convert Parquet file into a data frame into a CSV file or something like that, then I can do data translation for the user by stitching together a sequence of translations. This is a really interesting idea, and this graph here is from the Odo documentation showing you all of the different translators that were created for it. And so we liked this idea and we wanted to bring it back, but for sort of in-memory data structures. So what Metagraph includes is basically sort of a re-implementation of the Odo concept, where plugins can register the ability to translate from one data format to another. So we have a translator that knows how to go from a network X graph to a COOC graph, or a network X graph to something else. And so the automatic data translation is used in concert with the multiple dispatch. So if I am, say, calling an algorithm and I give it a network X graph, it will then try and find, first it'll try and find an implementation that requires no translation. That may not work. You may not be able to find an implementation that takes exactly the types you're passing in. In that case, what we'll have to do is then figure out, okay, what translators do we have? What is the minimum number of translation steps that will get me to an implementation that I can run? And that is currently, the heuristic is just trying to minimize translation steps. So if you have a function that takes 3 arguments and we have to translate one of them in one step, that has a cost of 1. If we have to then do, another argument takes 2 more steps, that maybe brings it up to cost of 3. So right now the cost metric is very simple. Again, sort of a placeholder, but we can get more sophisticated in the future. And I know Odo had weights on different edges, so you could actually decide which translations were more costly than others. And so that's something that we can expand into later. So one aside about how we had to think about this system and why we have these types and algorithms and translators and all this stuff is because one of the things that we saw when we looked at graph analytics in general is that there are a lot of different groups doing with different goals, and no one is trying to solve all of graph analytics for everyone for all hardware. And so it's important to be able to try and have a system where we can have people interact with just the piece they want. So for example, we might have one team, a researcher who's working on a better implementation of PageRank, sort of a novel algorithm for a well-known operation. In that case, all they need to do is write the concrete algorithm piece that connects their implementation into the Metagraph system. And now all of the Metagraph users would be able to take advantage of it and translate over and use it. Similarly, you might have another team that's taking a standard algorithm and just doing it on new hardware. Maybe it's a GPU, maybe it's a new kind of chip, that sort of thing. In that case, they might need to write a few more plugins, one to be able to move the data onto the chip, and another one to actually run the algorithm on the new chip. And again, they can hook that into the system, and then users can take advantage of the particular algorithm that they've optimized while doing all the rest of their work back on the plugins they already have. And you get other things, like people might invent entirely new APIs for users for working with graphs, or new, new optimized versions of things. And so the goal here is to allow basically different groups to work on a small piece of the graph problem and talk to each other, rather than have any one group have to be the library of all things. So another thing we include in Metagraph is actually a nice panel app that allows us to be able to explore the plugins you have installed in your environment. So if you have, the Type Explorer lets you go see, okay, what are all the graph implementations I have? And so on the system, we actually have 3. We have GraphBLOS, NetworkX, and SciPy. And I can see, the other types like data frames and node maps and things. What are all the implementations I have on the system? This is just handy for understanding what's going on. Similarly, there's a tab in there that lets you see, if I pick 2 types and I want to translate between them, what are all the translators available, and what route would the system actually pick to get from, say, a GraphBLOS node map down to a NumPy node set or something like that. And so this again is a really handy debugging tool for us to just graphically see what is the translator going to do when I give it this input and this goal. And then finally, it can put these things together and actually show you okay, I want to run this particular subgraph algorithm. I'm giving it a SciPy graph. What's it going to do? And so the solver will show you the different plans that are available and the one that the system would pick. In this case, doing a translation of the SciPy graph into a NetworkX graph to then call down into a NetworkX implementation. Another thing I think people don't necessarily realize that you can do, which we didn't know about when we started, is actually Dask collections have a visualize method that will show you things that you may have seen in other Dask talks that draw the task graph. You can customize this drawing quite a bit by passing in some special keyword arguments called function attributes and data attributes, which let you basically set graphviz attributes. So for example, we have a custom visualize method that we built on top of the Dask one that actually shows us translation steps different from algorithm steps. And it also draws the types of the values being passed through the system in a special way. And so this is something I think for people who are doing really extensive sort of Dask work, it's really handy to be able to control the visualization of a task graph. Last thing I want to talk about before I get to the wish list for Dask is about compiling Dask graphs, compiling DAGs, which is a part of the Metagraph system that we included in order to be able to support some of the more unusual hardware. We're doing this work as part of a DARPA project in conjunction with Intel, and they're working on a new chip to specialized for sort of sparse data structures. And so we ultimately are going to, for high efficiency, want to be able to combine tasks so that they can all run in one batch without having the Dask scheduler be involved in every one of them. So let's say we have a hypothetical Dask task graph, a hypothetical DAG, that we're loading some data frames, we're going to do some joining and filtering, and we make our graph, and then we do a bunch of stuff in Metagraph, and then finally we save the results. So this could be a DAG you might build in a notebook. And if we look at the Metagraph dispatch information, we might see that there has been registered with Metagraph some compilable implementations. So you can tag an implementation system basically and say, this can be compiled by this compiler backend. And these highlighted nodes might be in that category of they are compilable in principle. So then what we can do is look through the graph and find what are the subgraphs, safe subgraphs that we could choose to compile. And so much like actually what Dask will do, Dask will fuse linear chains of tasks to limit data transfer. We're currently doing the same thing where we are looking for linear chains of tasks that are fusible. And the goal is that you don't want to reduce the parallelism available to the scheduler. So we're going to say, okay, that top operation 1 and 2, that's going to be one subgraph. Operations 5 and 6 are another subgraph. You could imagine actually taking this whole subgraph and sending it off to some parallel hardware as one giant fused operation, but we're not doing that currently. So we pass those two subgraphs off to the compiler backend and then replace in the Dask task graph with a fused just-in-time compiled optimization. And this is what we actually hand off to the Dask scheduler to run. And in fact, we have a way to visualize this with the, these were just a kind of PowerPoint kind of diagram, but we have actually a way to see this in the actual Dask visualizer. So our custom visualizer will actually make compilable tasks into octagons so you can see them pop out. And then when they get fused, this is for a different graph, we'll actually indicate that these were fused by the optimizer before we run them. So we currently have backends that can do this for Numba and MLIR code. As a side to this project, we're working on how you compile graph algorithms with MLIR. People have interest in MLIR, come hit me up on Slack. But basically, this is what we're trying to use this system for. So let me in the last bits of this talk, I want to talk a little bit about things that we learned about Dask while we were doing this, and things that we wish Dask had an answer for, and maybe it does already. One of the things that I would love to find out is that some of the things I'm asking for actually exist, and I just don't know about it yet. So that's another thing to hit me up on Slack, is if you have an answer for some of these. So one of the things that came up while we were using Dask is it's not clear how to attach metadata to tasks. So a DAG is fundamentally just a dictionary of keys and tuples, and those tuples start with a callable. It's not clear where we should stick metadata in this system. So if I want to mark down some additional information about a task, where do I put it? Ultimately, the solution we came up with is our callables in the Dask task graph are actually objects that we can attach properties to. So they're not normal Python functions. They're other things that are callable that we can attach our metadata to. I don't know if this is what everyone else does, but I would love to know if there is a standard best practice here for how to attach this metadata to things. Another thing, and this is sort of a subset of the type information question, is if we're doing all this dispatch and compilers and all this stuff, type information is critical to be able to do this kind of work inside of a DAG. It's not clear where we could annotate the type of a task. Like, what is the return type of the callable in the task graph? If there was a place to stick that information, and maybe that's the metadata question, maybe there's something else, then you can actually analyze the task graph and do some of this compilation work. So should type information be a special property on the callable? Maybe we abuse Python type annotations to store this information. This is a question I'm sort of putting out there to the Dask experts, but it would be really great for other uses of Dask to be able to know where to stick types in a task graph. Another one is just a minor nitpick that, again, confused me when I was implementing a custom collection for the first time. It's unclear where args and keyword arguments should be handled, because by default, the tuple of arguments is being passed to the first item. If you have keyword arguments or keyword only arguments, ultimately what we ended up doing is every one of our tasks in the task graph looks like a callable, a list of arguments, and a dictionary of keyword arguments, and then we just pass it down this way. I don't know, does maybe everyone again also does this? Is this a convention that maybe lots of groups should follow? I'm not sure. Finally, is a little bit of a question about global optimization. So Dask has an internal, does optimizations on a task graph before running them, but they're currently collection specific, in that the Dask bag, the Dask array, the Dask data frame, and the Dask delayed all have their own custom set of optimizations they apply to the DAG before execution, which is useful because you maybe want to do different things. But the problem is which ones are used is determined by the final computed object. So if I have a whole task graph that I start with an array, go into a data frame, and maybe end in a delayed Dask delayed function, and then I compute that final thing, the only optimizations that are run are the ones that are registered for delayed, not for data frame or array or anything previous to that. And it's not clear how to register global optimizations you want to apply to every task graph. So we eventually just had to solve this by making our own optimize function that users have to invoke manually. And to this point, there's actually an open issue in the Dask issue tracker from Jim Christ from last year, noting this problem actually, that if you end in a delayed object, the current optimizations for delayed are all, very, very minimal. And so you actually don't see a full optimization of the graph if you end with a delayed object. There was no solution to this currently, but we see this basically to have the same question in a different context. So to conclude, our goal with Metagraph is we're trying to make it easier to combine multiple graph libraries. I encourage you to go check out the docs. We have tons of example notebooks and other things. The goal of this talk was really more to talk about the Dask interface than Metagraph itself, but if you have an interest in graph analytics, go take a look. One thing we're experimenting in Metagraph that I think is of interest to the broader Dask community is doing things like combining data translation with multiple dispatch, trying to figure out how to make an open-ended API ecosystem with plugins, and how to do partial compilation of DAGs in Dask. We may spin out the core of Metagraph someday into some other package because it's not really graph specific, even though it's motivated by graph analytics as a use case. And we're very interested in if there are thoughts in the community about how Dask wants to add more structure for tasks and also how to enhance optimization in Dask. So I think that is it. So we have time for questions.
Yeah, thank you, Stan. We do have time for a few questions. We have one question that John Moore asked. Could you explain more about the boundary between distributed graph computing, not inspired by Dask, and parallel task execution? Example, is placing tasks on workers considered as one of these or the other?
That is an interesting. I'm trying to parse this because again, there's a lot of different graphs flying around here. Let me see. So yeah, so distributed graph computation is in like I'm trying to do computation with a Dask, or sorry, I'm trying to operate on a graph in a distributed fashion. That's an interesting problem, and there are a small handful of libraries that try and tackle it. Oh, see, this was the other comment about what was inspired by Dask and what was not. Not sure if I know exactly. I would say if you can hit me up on Slack, I might be able to answer this better. I'm not 100% certain I understand the question.
Okay. I have a couple more minutes for a few more questions. Oh, Matt commented. Let me see.
Oh, do I get to talk?
Yes.
Okay.
I'm sorry, I'm not sure how
Hey,
that
Stan.
happened.
Hello.
Yeah, great questions. I actually really want to talk to you after this, if you're free. In the Slack channel, Summit Talks, I put a few links to issues you might find interesting. There's a lot of really exciting work happening right now around high-level graphs in Dask, which might be a really good place to put a lot of this metadata. We've actually already started putting some metadata on there to help with things like advanced visualization, kind of like the stuff that you guys are doing with Graph Viz, but like how can we extend that to D-types, chunking, et cetera. I think the high-level graphs end up providing a lot of space for metadata to live that I think will be a good place for you all to engage. I also think that you all are also really, really good at this kind of graph manipulation compiler thinking. And so I would love to try to nerd snipe you into really owning that effort in the Dask system. So I'm really excited to talk more about this with you.
Cool, awesome.
Sweet. I think, John, if you want to follow up too, we still have 1 minute.
Okay, yeah. So what I was trying to get at was, I think in one of the early slides, Stan, you mentioned things that Dask brought to the table, in terms of
Oh, yes.
data frames and arrays and so on. But you said it doesn't bring, or we are not bringing from it. Yeah, exactly. Thank you.
Yep.
And the partition graph computation. So I was just wondering what was, on each side of that boundary, as it were.
Yeah. Yeah. So basically what this means is that metagraph operations do not generate a whole group of tasks. In order to say, like, if you're doing PageRank, we don't generate out a whole distributed set of tasks to do PageRank. We just call down to a library that does it. If that library happens to be distributed, then it's free to do that. But at the metagraph level, we're not trying to figure out how to chop up a graph algorithm into pieces to distribute out. So what that means is that there is a potential for, you might do a lot of data prep with Dask, at the data frame level where you're, loading and filtering and joining. But once it comes to actually metagraph, we're going to bring all of that down to a single node unless that backend knows how to run stuff in parallel. So this is mainly because the current use case we have, or we're targeting again, is this custom Intel hardware, where that model works, but that may not work for everything.
Thank you.
Sorry, Stan, thank you. Yeah, I'm gonna ask that we continue the conversation over in Slack since our next speaker is here. Thank you, Stan.